Okay. Hi guys. So can everyone hear me clearly? Okay. So let's begin. So now we're going to talk about complex numbers, and we are going to start from the basics of mathematics. So we have, first of all, a set of positive integers. Well, some people denote this to be the set of non-negative integers, which is also fine. And then we have integers, rational numbers, real numbers. And let's just stop here. But there are other number systems as well, such as the mod p numbers, the p-adic numbers, and so on. So let's begin first by, well, we can think as mathematicians instead. So instead of defining these sets intuitively, like if I ask you how do you define the set of natural numbers, you might give like a very vague answer, 1, 2, 3, 4, 5. I mean, it's not very vague, but for from a logical point of view, it's quite vague because like what do you mean by 1, 2, 3, 4, 5? Like what comes after 5, for example? So to define the natural numbers, there's something called the piano axiom, the piano axioms. Which is a set of axioms, right? And including the axiom that 0 exists, the axiom that if n is a natural number, then there's a successor of n, which is also a natural number. Sorry, let me drink a sip of water. And so on. There are quite a few statements for piano axioms, and that would uniquely define the set of natural numbers. And from here onwards, there's a lot of complicated extensions. So from n to z, how do we go from n to z? It's where we force ourselves to subtract any number, right? In fact, we can write this as an equivalence class actually. Like a minus n, z is actually a set of a minus b such that a and b are in n, and a minus b is equals to c minus d if and only if a plus d equals b plus c. Well, that's one way you can do it. Of course, I'm being very vague here, actually. I mean, a little bit more logical, but then still not logical enough to be formal. So from Z to Q is where we allow ourselves to divide. So it's like the equivalence classes of A over B. I'll not write that down. In fact, if you're interested in all of these things, you can read, and I strongly recommend, Analysis 1 by Terence Tao. It's quite nice. So it explains all of this. But anyway, from Q to R, that's a very complicated thing. There are multiple ways to extend from Q to R and what R really means. So, well, in the book by Tao, he defined it this way. So this is one of the definitions. So it's about completeness. So completeness means that any sequence that gets arbitrarily close to each other must converge. So for example, For example, square root 2 is not in Q. Square root 2 is not in Q, but it is the limit of this sequence. I'm not sure if I have it in the notes, but a naught equals 2, an plus 1 equals, let me, for, I think it's an over 2 plus 1 over an, if I'm not wrong. This sequence converges to a number whose square is 2. So this sequence converges to a number whose square is 2. So that's not in Q. And that would be, if we force every such sequence to converge, then that's what we call completeness. So R is actually the completed version of Q. There are other definitions of R. For example, like it's a set of all things that you can write as decimal 0 point blah 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 blah, except if you have a trailing infinite number of nines. That's another way. But that's not the point for today. Today I want to talk about complex numbers. And as some of you have mentioned, something else called quaternions. Well, I'm not going to talk about that today, but it's well, something related to this, how we extend numbers from Q to R to now we're going to do this. So what do we do to extend to C? So for example, from N to Z, we kind of define this new number called -1, such that it's an element where after you add 1 it's 0. So don't think of -1 as like, I mean, sorry, you should think of -1 as like an object where if you plus 1, you get 0. And then from Q, from Z to Q, maybe you have like objects like one, like division, like let's say 1/2. So 1/2 is an object where after you times 2, you get 1. And then from Q to R, maybe you have square root 2. So square root 2 is an object where after you square it, it will be equal to 2. Sorry, after you square it will be equal to 2. I mean these are just examples. But the thing is, we want them to be satisfying some kind of polynomial. Like as you can see, this is 2x equals 1, this is x squared equals 2, this is x plus 1 equals 0. So the thing is, if we introduce this new number I, such that I squared is -1, so basically x squared equals to -1, we should get something called C. And well, let's see. No pun intended. So if I add a single term I into R, I mean we get this, right? Which isn't really useful. You just add a single element into this set of real numbers. Well, very not useful. But if we allow ourselves to add things, to subtract things, to multiply things, to divide things, right? That means if I is inside, then I plus I is inside, I plus 1 is inside, 2 times I is inside, I times I is inside, and so on and so forth. What you would expect is that all numbers in the form a plus bi, where a and b are real numbers, should be in the set, right? Because if I is inside, then b times I is inside. And if b times I is inside, then b times I plus a is also inside, if we allow us to use all of these operations. So Now we have this set a plus bi, where a and b are real numbers. And why is this good? Now, let's see. If we add two numbers of this form, like 2 plus 3i plus 4 plus 5i, then you get 6 plus 8i. Is a... I'm not sure what symbol that is. Can you like explain that symbol? Like, what's this? Argand diagram. Oh, well, we'll get to Argand diagrams later. But I'm not sure what you mean by this. Okay, anyway, so we have this set now. Does this set obey our rules? So if we add two numbers of the form a plus bi, like 2 plus 4i plus 3 plus 5i, we get 6 plus 8i, which is, yes, it's also in this form, a plus bi. How about if we subtract? We should also probably see that it's also of this form. 2 pi over 3 is 1 plus. Well, it's just a, I wouldn't say, I would say it's just a shortcut notation. It's still a complex number. It depends on how you define that symbol, actually. Like, as you said, that would be 1 plus square root 3i. That means it's just a different way of writing the same number. So yeah, if you, well, depends on how you define it. You can say it's a complex number as well. So when we talk about complex number, we're talking about the number itself, like whether this thing is a thing. It doesn't matter how we write it. Like if 1 plus 3i is a complex number, would you say that 1 plus 2i plus i is not a complex number? You're like, no, right? So they are all complex numbers. It doesn't have to be actually explicitly written in the form a plus bi. So and if you multiply two numbers of the form a plus bi, c plus di, is it of the form something plus something I? Let's see. If you expand this, ac plus bdi squared plus adi plus bci, well, but I squared is minus 1, so ac minus bd plus ad plus bc times I. But yeah, so it's a real number plus a real number times I. So nice. And how about division? Does it give us a number in the form something plus something I? And this is a bit harder, but it's still doable. So a plus bi, what I do is I multiply by the conjugate, which I will define later. It's basically this thing, c minus di. Well, you expand this thing. On top, you get ac plus bd plus bc minus ad I over c squared plus d squared, apparently. So c squared plus d squared is a real number. So we can just literally write this as this fraction, ac plus bd over c squared plus d squared plus the fraction bc minus ad over c squared plus d squared I. So yes, again, it's in the form of a real number plus a real number times I. So this is basically what we all need. That's all we need for us to do very nice operations on it: addition, subtraction, multiplication, division. So as long as we added this new object I, whose property is I squared equals minus 1, you get this whole new set. And by the way, if a set satisfies this nice property, like addition, subtraction, multiplication, division, it's called a field, if you're interested to know the name. So you can say the set of complex numbers, you can say the field of complex numbers. But you cannot say the field of natural numbers, because you don't necessarily get a natural number after you divide two numbers or even subtract two numbers. Okay, but of course, when I say division freely, I mean like any division, but except dividing by 0. except dividing by 0. So in this case, can we see is dividing by 0 the only exception that we cannot do? And apparently yes. So the only thing where this thing breaks down is where c squared plus d squared is 0. But c and d are real numbers, so they are both 0, and hence you are dividing by 0 in the first place. So yes, you can still do division freely, except when you're dividing by 0. Okay, so that's the introduction of this set. Yeah, the set of rational numbers is also a field. The set of integers is not a field because you cannot divide. The set of real numbers is also a field. Okay, so some people might write this thing, I equals the square root of -1. Well, I don't really like to start with this definition. In fact, I think it is quite confusing to put I equals square root of -1, because there will be quite a few problems that arise from this. Because first of all, you don't even know what the definition of a square root is for negative numbers. So how do you write this as that? And second of all, you will see afterwards that a square root function is quite hard to define for a general complex number. So I wouldn't write this. In fact, you can write this afterwards, after you learn about something called a principal root. But if not, I don't like to start with this. I will say I is just an object whose square is -1, and that's all. So this is just the definition of I. Nothing else. Okay. So I won't write this, even though it's correct in some sense, but only after we introduce some definitions of what this square root really means. So for now, I is just a number where I squared is -1. And also, I will also be careful in what I say. So if I have, like, let's say -I, notice I said -I, not -I, because if I said -I, it's kind of like saying this thing is this is a negative number, which you cannot really say what a negative number is in complex for a general complex number anyway. So yeah, so I'm going to be quite precise in my wording as well. Okay, so back to the topic. Now, a general complex number z can now be written as a plus bi, where a and b are real numbers. Okay. So a, we can write it as the real part of z, and b, we write it as the imaginary part of z. Okay. Well, these are just definitions. So it's called the real part and the imaginary part. So if we say two complex numbers are equal, so A, B, C, D, of course, I'll also be so precise. I should also be precise. I should always write this, because if let's say D was I, for example, oh, why do I write Z? But it's kind of like a preference, personal preference, I think. I mean, it's one stroke, so that's, if I do this, I have to do two strokes anyway. So this is if and only if A equals C, B equals D. Okay. So a complex number is completely specified, all right? Completely specified if you give the real part and the imaginary part. Okay? It's completely specified by two real numbers. So this should remind you of something familiar, which is the Cartesian plane, like Cartesian coordinates. If you are in a Cartesian plane, on a Cartesian plane, every point on the plane is specified also by two real numbers, right? The x coordinate and the y coordinate. And complex numbers z specified by a real part and imaginary part. So let's combine these two concepts together and construct what we call the complex plane or the Argand diagram. So the complex plane is just a plane where you label the horizontal axis as the real axis instead of the x-axis and the vertical axis as the imaginary axis instead of the y-axis. So if we have 2 here and we have 1 here, then this point would represent the point 2 plus I, for example. And well, that's basically the whole thing. In that way, every single complex number is represented by a single point on this plane, and it goes both ways. Okay, so it's kind of like a quite a nice thing, because for real numbers, you specify them with a line, right? For real numbers, you specify them on a line. They are, what I can say, one-dimensional numbers, whereas complex numbers are kind of like two-dimensional numbers. You need 2 real numbers to specify them. So number line, number plane. Okay, using an Argand diagram, we can kind of do quite a few things. So for example, we can talk about the magnitude of a complex number or the absolute value of a complex number. So if z is a plus bi, I define z absolute value to be the distance from 0. So if it's like 2 plus I, what's the distance from 2 plus I to 0? It's 1 here, it's 2 here, so that's square root 5, right? That's square root 5. Z equals 2. Yeah, exactly. So square root 5. Well, how do we do it in general? A plus bi, what's the distance from the origin? Or from 0? It's just by the Pythagoras theorem, the square root of a squared plus b squared, right? So that's why I define as the magnitude of a complex number, which actually agrees with the definition of the absolute value in real numbers as well. Like, why do we say a negative number under the absolute value becomes a positive one and a positive one stays a positive one? Because they are all just describing its distance from 0. It's just that for real numbers it's on a line, so it doesn't really matter. Okay, so that's absolute value. Now, how about the argument? So the argument of a complex number, it's kind of a weird name, but at least that's what people use. The argument of a complex number, first of all, I would like to define it to you on the complex plane first, because it's much easier. Someone said theta equals tangent inverse. It's a bit more subtle than that. It's a bit more complicated than that. So because tangent inverse only gives you values from minus pi over 2 to pi over 2. So if a complex number is here, or here, or here, or here, or here, what I say as the argument is the angle calculated in this direction from the positive x-axis. So that, well, these angles basically. And if it's on the other way, I can do it as a negative angle. So these are arguments, and we normally write them in radians. So the angle, well, this angle, I think I shouldn't write it down. I'll just give some examples. So, for example, 1 plus I 1 plus I is here. And the angle is 45 degrees, so that's pi over 4. Is it pi over 4? Yeah, pi over 4. And also we require, normally, just for convenience, require the argument to be from pi to pi. I mean, you can work in systems where you work in 0 to 2 pi, but again, that's just a preference. It depends on you actually. What matters is that the argument should be mod 2 pi. That's all it matters. But for usual reasons, if you don't mention anything, we'll just require argument to be from minus pi to pi. So either from here to here. Okay. So that's the argument. And someone said the argument of a plus bi can be the tangent inverse of b over a. And as I said, it's a little bit subtle than that, because it's a little bit more subtle than that because it works for the first and fourth quadrant. That's what I can say. It works for the first and fourth quadrant. But for here, you have to kind of add pi or minus. Let me think. I think you have to add pi, yeah. So it should be, if you want to write it really specifically, it should be something like that. Either tangent b over a or tangent b over a plus pi. So this is if a is more than 0. This is if a is less than 0. Yeah, something like that, if you want to really be precise. But the geometric interpretation is much better. The geometric way of defining it. Okay, so magnitude and argument. So all clear. Any questions, any confusions that you would like to ask? I would answer them immediately. Okay, if not, we move on to the complex conjugate. Argument is any point in a complex. No, argument is the angle. It's the measure of the angle if you draw a line from that point to the origin, and then you measure this angle. So in that sense, the argument of 1 plus I is the same thing as the argument of, let's say, 2 plus 2i, or even the argument of I don't know, 7 plus 7i. Where is 0? The 0 is here. 0 is 0 plus 0i, right? This is 0. The point specified by 0. But remember, in complex numbers, for complex numbers, a complex number is represented by a single point on the complex plane. A single point on the complex plane. Well, okay, you're asking the argument of 0. Good question, because we don't really define argument, because it doesn't make sense, right? If you want to ask for argument of 0, normally we just avoid that case. Well, a singular point without an argument is still fine. We can still do a lot of things with this definition. Is it the x-axis? What do you mean, is it the x-axis? 0 radians in argument is that well, you're half right. So the locus of points where the argument is 0 is the positive x-axis. It's the positive x-axis. The positive x-axis. For the negative x-axis, you say the argument is minus pi. Well, or pi, or 3 pi, depends on yeah. So that's basically what it is. Again, argument of 0 is undefined. It won't hurt us as much. We can still do a lot of things to it. We can still do calculus on complex numbers, even with argument the undefined at a single point. Well, they're called singular points. But anyway, so the next one is called complex conjugate. and I already said it just now already. In fact, so the complex conjugate, well, some people use an asterisk, some people use a bar. Again, that's up to you. I should write it in a different color, otherwise you might say it's a Z star over Z. Okay, so the conjugate of Z will be A minus BI. A minus BI. So anyone can tell me very quickly, what does the conjugate mean if you're looking at the points on the complex plane? What does it mean when we conjugate an element? Well, no, I mean like if this were 2 plus I and we consider the conjugate of 2 plus I, where would it be? What happens to the point? Reflect across the x-axis. Yes, exactly. So applying conjugate means to reflect across, sorry, real axis. I shouldn't say x-axis, real axis. So remember, this is not the Cartesian plane. So we don't say x and y axis, we say the real and imaginary axis. Okay. So that's conjugate. Okay, so one simple property, as you can verify, is that Z times Z bar is equals to the magnitude of Z squared. So anyone can tell me why? Just very quickly. Multiply, so yeah, exactly. So they are both equal to, well, if Z is A plus BI, they're all equal to A squared plus B squared. Yeah, and then you remember I times I is minus 1. Okay. Now, let's look at the geometry of complex numbers, even though this is an algebra class, but it's worth mentioning that there's a lot of geometry behind complex numbers. So we already seen one property just now. If you apply conjugation, we essentially reflect across the x-axis. So let's see what happens for more properties of complex numbers. So addition and subtraction is quite easy. So if you've learned vectors before, in particular two-dimensional vectors, complex numbers can be seen as a two-dimensional vector, basically. So for example, if we have 2 plus I, and maybe we have what should be a nice candidate? Let's say I don't know, let's say what's this? This is 2 plus 2I. What happens when we add them up? When we add them up, we get 4 plus 3I. 4 plus 3I. So that's somewhere here. 4 plus 3I. So if you learn vectors, you can immediately see that the new vector is just the sum of the two old vectors. Right? The red is equals to the blue plus blue. Yeah, because you add the real parts and you add the imaginary part. And that's the same thing as you adding two-dimensional vectors. You just add the x component and you add the y component. So same thing here. And subtraction, well, same thing. If you wanna flip the sign of a complex number, it just means you flip the direction of the vector. So addition and subtraction are easy. Now, let me see if I want to talk about multiplication now. Yeah, so I'm going to talk about multiplication. Multiplication might not be so obvious at first. In fact, it's very not obvious at all. because you already know you cannot multiply two-dimensional vectors directly unless you define like dot products or cross products. But those don't give you a nice answer. So multiplication of two complex numbers. Let's just try an example first, right? In fact, let me just enable a grid system. Now, anyone tell me two simple complex numbers? But not simple until you give me like two real numbers. Anyone just give me two complex numbers that I can easily draw on the plane. Okay, 1 plus square root 3i. Okay. Okay, you seem to love that number a lot. Okay, let me look at the grid. Square, let's say help. Okay. Yeah, that should be better. Okay, another one. So one of you gave 1 plus square root 3i. Oh, it's a 3. Square root 5 plus square root 2. Okay. Okay, sure. Okay, so let me think a little bit. Let me think for a moment where the product would be, so that I can draw the axes nicely without wasting space. Yeah, I think I can just draw like that. I won't touch the negative part. So 1 plus square root 3 is somewhere here. 1 plus square root 3. If I draw an arc here, square root 3 is somewhere there, right? 1 plus square root 3. I. Okay. Square root 5. Square root 5 is about, I know square root 2 is about 1.414. So that's somewhere here. And square root 5. I mean, these two differ by a factor of, oh wait, no, they don't differ by a factor of square root 3. Square root 5 is about 2 point something. So maybe probably here. Okay. Let's multiply them the algebraic way first. I'll just speed it up. So it will be this minus this plus. Can anyone take out a calculator if you have one? And kind of calculate these values for me? Well, just for the purpose of describing this on the complex plane. Square root 2 plus square root 15. I. Square root 5 minus square root 6 is what? Minus 213. That shouldn't be it, right? Okay, let me just use my calculator. Square root 5 minus square root 6. Negative 0.213. Okay. Negative 0.213. And then the other one? Square root 2 plus square root 15. Square root 2 plus square root 15. 5.29, right? 5.29. So where is this roughly? It's roughly. In fact, let me see what square root 5 is, just to make sure I plotted that point correctly. 2.24. 2.24. Oh yeah, close enough. Okay, minus 0.2 is somewhere here. 5 is somewhere here. So this is the product, okay? U, V, this is U, this is V, this is UV. Okay. Okay. Hold on. There we go. So you might not see any pattern whatsoever from this thing. You have a U, you have a V, suddenly you have UV. So let's not talk about how these interlink with each other, but we are going to try to use another form of notation to write complex numbers. And so before I talk about the geometric interpretation of multiplication, we are going to use what we call polar forms to write the complex number. So if the magnitude of a complex number is r and the argument is theta, then you might recall from, if you've learned polar coordinates or trigonometry in general, the x coordinate is always r cos theta and the y coordinate is always r sine theta. So if you've learned trigonometry, you should know this thing. Like cos theta is the adjacent side over the hypotenuse. Of course, that's for angles in the first quadrant, but for the general form, it's just, well, kind of the same thing. So like cos theta is always equals to the x coordinate over the distance to the center. Does argument U plus argument V? Yeah, I'll come back to that later. But yeah, that's true. Well, mod 2 pi. Okay, let's cut back here. So that means Z, which is x plus yi, can now be written as r times cos theta plus I sine theta. Okay. Anyone not very familiar with trigonometry, like cos theta, sine theta, or is everyone here fine with what I'm writing here? I can spend a little bit of time talking about. Okay, fine. Okay. So any complex number can be written like that in terms of its magnitude and argument, right? So again, it's still two real numbers. So that's something cool about this. So there are still two-dimensional numbers. Even if you change another way of writing them, you still need to specify two real numbers in order to specify a complex number. Just that just now it was the real and imaginary part. Now it's the magnitude and the argument. So they're still two-dimensional. Well, in that sense, I won't really define to you what two-dimensional means. That's really a casual way of saying it. So this is a polar form. Now, let's see what happens when we multiply two complex numbers. Let's say one has magnitude r and argument phi, and the other one has magnitude little r and magnitude theta. Let's see what happens when we multiply them together, right? Let's see what happens when we multiply them together. And we will see something very, very interesting. Z1, Z2. So the r's, well, multiply. Now I'm going to use a shortcut notation. This is cos phi plus cos theta. That's cos phi cos theta. And then these two multiply up to minus sine phi sine theta. And then for the i's, this one is sine phi cos theta plus this one. So that's sine theta cos phi. Okay. Now, here is where we're going to use our mathematical culture. Well, cos theta cos phi minus sine theta sine phi. If anyone's very fluent in trigonometry, does anyone recognize what this is? Yeah, the cosine addition formula. Of course, if you don't know this, it's okay, but you can read it out afterwards. So this is basically just cos theta plus phi. And the other one is just sine theta plus phi. Now, what can we see here? Where where is my pen? Okay, there we go. What can we see here? Remember how we write complex number like that? This is the new magnitude. The new magnitude. This, well, look at it, it's the same form as that. It's just that the angle has changed. The argument is now theta plus phi. Therefore, what we can say geometrically is that when you multiply two complex numbers together, the magnitudes will multiply and their arguments will add. Does that make sense? So it's quite non-intuitive to see how this happens, but the maths tells us it works. So what it's saying is that, so what's the length of u, for example? The length of u is 1 plus, it's exactly 2, right? 1 squared plus square root 3 squared square root, that's 2. And then the other one, 5 plus 2, that's square root 7. Yeah, square root 7. And if you kind of calculate the magnitude of this, it is indeed 2 square root 7. And if you look at the angles, this new green angle is just the sum of the two blue angles. The sum of the two blue angles. And that's very, very interesting. That allows us to do a lot of geometry. In fact, there's a whole technique of solving geometry problems using complex numbers. So for example, I mean, it's one of the Bashi methods. Like the top 3 Bashi methods are Cartesian coordinates, complex numbers, and also barycentric. So that's why there's a lot of geometry behind this. If you multiply 2 elements, you get this kind of relation. So if you're familiar with geometry as well, this means the function of multiplying by a complex number, is just literally applying a spiral similarity to the plane. So it's like this maybe. It's applying a spiral similarity to the plane at some angle. So become like that. Let me draw this carefully. So that's what happens when you multiply by a complex number. You will get a spiral similarity. Okay. So far so good. Anyone has any questions before we move on? If not, I'm not going to discuss the geometry part of the handout. There are 3 problems there that you can think about, but they don't require any extra knowledge. You can just use this knowledge that you have, like multiplication. You multiply 2 numbers, so, add the arguments. This is because you move 1 to a complex point and all the points from the multiplied. Yeah, exactly. What you're saying is correct. So when you multiply by a fixed complex number C, what you're essentially doing is to bring 1 to that complex number C, and everything else just kind of tilts according to this transformation, if that makes sense. Right? Yeah, so as you can see, I kind of position 1 and C with respect to this smiley face quite nicely. Okay. What I mean just now was like, if I have a flower, let's say a flower, then it will be like this now. something like that. Okay. So I'll not discuss the geometry part. It's quite fun as well. You can think about it, especially the 3 squares problem that I have put in the handout. It's really, really interesting. And if you solved it, you can also see it shouldn't make sense, but it does. It works. It's maths. Okay. Now let's move on to the more algebraic side of complex numbers. So let's look at the conjugate function again. Revisit. So the thing is that conjugation is actually a really, really good operation. It behaves very well under addition, subtraction, multiplication, and division. So let's see what I mean. If a plus bi and c plus di, I conjugate them, I get a minus bi and c minus di. But then I multiply them, I would get ac minus bd minus bc plus ad. Oh yeah, you can use the geometric interpretation to look at this property as well. But I'm just going to prove it algebraically. Well, just for once. But what happens if you first conjugate them first? That means, oh sorry, I mean already. What happens if you multiply them first? Then you get AC minus BD plus BC plus AD I, and then you conjugate. You'll see that they give you the same thing, whether or not you conjugate first or you multiply first. So that means U times V conjugate the same thing as U conjugate times V conjugate. In fact, you can prove every single case. U plus or minus V conjugate is equals to U conjugate plus or minus V conjugate. And for division, you can also try it out. So it behaves very, very well. Yeah, you can draw this using a commutative diagram. And in fact, it's a nice word for such a function that obeys closure unto addition, subtraction, multiplication, and division. It's called an automorphism. But of course, I'm not going to use that word. It's a word very well. Multiplication is still not that good because if you multiply by uv, you don't multiply by both u and v. Like if you multiply by 2 here, 2uv, you cannot say it's the same as 2u times 2v. So conjugation is even more delicate. So that's why there's a nice name to it. It's called an auto. Now auto exponentiation also doesn't work for this one, for the addition case. Right? If you a plus b whole thing squared, it's not the same thing as a squared plus b squared. In fact, the only automorphism in complex numbers is just the identity function and the conjugate function. So the function of just doing nothing or the function of applying conjugate. That's the only two functions that are automorphisms. So basically they fulfill all of these things. But yeah, I'm not going to use this word anymore. It's just a very fancy word that maybe I just want to bring it up. Okay. So now let's look at the exponential form. And this one is what I will say even more mind-blowing. So we're going to revisit the exponential function just now. This e to the x is equals to 1 over 0 factorial plus 1 over 1 factorial. In fact, I'll just use what people would normally write. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus blah blah blah. So this is a power series that works for all real numbers, right? It's not like the geometric series where you have to require x to be less than 1, more than -1, right? There's this radius of convergence, we say. But this function, e to the x, and this power series works for all real numbers, all of them, including large x. Of course, to prove that, you have to use a little bit of real analysis again. So I can write this as this if I'm lazy. So that's xk over k factorial. And let's also revisit the sine function and the cos function. They also have their own analogs, which you can read it out on the Maclaurin series or Taylor series. But it is something like this. I don't require you to know all this or to prove this, but I'll just write it out first, and I will give it to you as a given. So later you will prove something else, and I allow you to use these identities. So that's the sine function. Cos function is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus blah. Okay. Oh yeah, fun fact. You know, people normally say when x is small, sine x is approximately equal to x. That's why. Because the first term of sine x in this series is x. And then afterwards it's like very large powers. For small x, this kind of go negligible. That's just a fun fact. Okay, we'll come back to the topic here. So sine x and cos x. Yeah. So sine x over x is 1 for limit x to 0. Okay. Now, here's a very interesting move, but also a very bold move. In complex analysis, basically the result is that this also works not just for real numbers, works for complex numbers as well. That basically means if you plug in a complex number here into any of these, they all converge. So I mean, like, I shouldn't say work. Like, maybe I'll say converge. In fact, it's not hard to prove as well, but it's quite technical. You have to use some kind of, you have to bound the size and then do a ratio test. But the point is that they all converge for complex numbers too. That means I can plug in complex numbers to these functions. And of course, just as a side note, some people might say this doesn't make sense. I'm raising e to the power of a complex number. What does that even mean? Right? So here is where we have to kind of accept a truth that is, once we write e to the x as this form and we allow to plug in complex numbers, we don't really see it as literally a number 2.718 raised to some power. In fact, if I ask you e to the power of pi, it doesn't really make sense anymore. But rather, it will be a function that satisfies this e to the x plus y equals e to the x times e to the y. So from now on, think of this e to the power of x as just a function. Don't think of it as some literal number raised to some power, because that doesn't make sense anymore when you plug in some non-integer values, right? Just think of it as a function that satisfies this property. So now, the point is, you can plug in complex numbers. And now I would invite you to afterwards try and prove this interesting result. E to the ix is equal to cos x plus I sine x. This is called Euler's formula. So one of the results is what many people would say in mathematical pop culture, e to the I pi equals -1. Because if you put x equals pi, you'll get -1. And yeah, that's true as well. But the more general form is this: e to the ix is equals to cos x plus I sin x. Use calculus. Yeah, you can also probably. Yeah, but okay, yeah. So but if you want to prove this identity using complex numbers, you have to make sure you are allowed to integrate complex functions, right? So yeah, so you have to be a little bit more precise as well, because some complex functions are not integrable. That means you cannot really integrate it. But apparently all of these power series, they are integrable, so you can do such a thing. But to be very precise, you have to read up real analysis and complex analysis. But of course, Olympiad syllabus doesn't really require that sort of technicality. So the point is, you can prove this just by using the power series here. E to the ix equals cos x plus I sin x. Okay. Now, once you know this, remember just now we said every complex number can be written as r times cos theta plus I sin theta. Now, I can just write this as er times e to the I theta, even shorter, an even shorter form of writing a complex number. But again, you still need two values, you still need the magnitude, you still need the argument. But it doesn't matter. But what matters is that we have found an even shorter way of writing a complex number. Okay. And also, you can also immediately prove this fact. When you multiply two complex numbers, you get a complex number where the arguments add. So can we see? What about complex to the complex? Now, yeah, so that will be undefined. So for example, you might have seen people saying what is I to the I. In fact, I wouldn't really say there's an answer to that. Okay, hang on. Because first of all, what do we mean by I to the I? What do you mean by to the power of I? Like for general numbers, like for e to the I, that's fine because we already have a function defined just now. What's e to the x? This literal power series, right? But for a general complex number, how do you define its ith power or its x power? In fact, it's a very hard thing to do, and some people say the I to the I is e to the what again, to the pi over 2i and then power I. Well, pi over 2i because the argument is pi over 2, right? And then they say this is e to the minus pi over 2. So this is wrong for many reasons. Again, the first reason is, as I said, we haven't really defined what to the power of I means for a general complex number. And I think we cannot really we cannot really give a very nice definition. And second of all, this is not the only way to write I, right? You can write it as e to the pi over 2 plus 2 pi I. And after raising by I, you get a completely different number. Completely different number. So it doesn't make sense. All of this doesn't make sense. If you see this kind of thing, just ignore it. It's not real. Yeah, no pun intended. but well, maybe you can create a system where you can talk about powers of I, but then you will have to abandon a lot of rules that we already know. For example, what we did here, perfectly reasonable rules, but we get two different answers. That means if we want to create such a system, we have to abandon a lot of rules. So yeah, so let's get back to the topic again. I've been digressing a lot. Sorry. Okay, now, any questions so far? Yeah, log I also. Okay, logarithm. Well, you can define logarithm in complex numbers, But again, you have to be precise as well. Logarithm. I think there's a number of, sorry, there's a name for complex logarithm. I forgot what it is really. But anyway, yeah. Let's look at the next section. And the whiteboard is getting quite full, so again I'm going to restart the whiteboard. So as I'm restarting the whiteboard, I'll just continue talking. The next section will be talking about polynomials. So we're going to incorporate what we've learned. So this is the most beautiful thing of complex numbers, which is something called the fundamental theorem of algebra. Fundamental theorem of algebra. So I'll state the theorem first. If we have time to prove it, we will, but probably we don't. So it says I'll just write it in maths notation. Any complex polynomial, so polynomial with complex coefficients, which includes polynomials with real coefficients, includes polynomials with integer coefficients. So basically kind of all of them. Any complex polynomial can be factored completely into linear factors. So that means anything can be factored into r minus x minus something, x minus something, x minus something, blah 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 blah, and then maybe times a constant at the back. Constant. So any polynomial. Of course, these roots might be very complicated complex numbers, but they are still complex numbers, they are still constants. In fact, there's an equivalent statement to that. Any f has a root in C. Well, at first glance, you might say the second one is just a special case of a special result of the first one, right? If we have so many roots, that means it has a root, apparently. But you can actually prove the other direction. If any polynomial has a root, then you can prove the first statement, which seems like the stronger statement, but apparently they are both equivalent. Can anyone see why? Why does the second statement imply the first statement? So think about what you've learned in the previous lecture. What happens when a polynomial has a root, and what happens afterwards? Anyone? X minus r divides fx if and only if fi equals 0. Okay, and then how do we get like so many linear factors if the second statement were true? Of course, we haven't proved that it's true. I'm just saying, if you've proven the second statement, how does it imply the first statement? So if there's a root, that means fx equals x minus r times gx, right? For some polynomial g. For each root corresponds a linear factor. Well, what you're saying is this direction, right? Each root. But what if there's no roots? Like after you have one root. Yeah, each root corresponds to a linear factor. But can you go the other direction? If any polynomial has at least one root, this statement doesn't tell you that any polynomial can have like n roots, right? You just say has a root, has one root. Yeah, so it really seems like a very weak statement of the first one, but apparently you can prove it back. So the point is this: if this statement were true for any polynomial, so note any here, that means if this were true, okay, so we write it as this, we apply the same theorem, I mean the same statement, onto this polynomial now. You apply the same statement to this polynomial. So gx has a root also. And then maybe hx. And then you apply it to this one again, and so on and so on and so forth. In the end, you will use up every single degree. And therefore, you have proven the first statement. So if the second statement were true, you can prove the first statement. Okay? If we have time, we're gonna prove the second statement. How do you know gx has a root? Well, because I assume this statement is true, right? Any polynomial has a root. Well, gx is a polynomial, so gx has a root. Yeah. So it's like repeatedly arguing the same theorem, which you know is true. I mean, I assume it's true. I will prove it to you afterwards if I have time. Okay. So again, like this is kind of like a nice thing to learn as well. If you can kind of reduce a problem into a much simpler statement, it's much easier to prove. And it's much easier to prove the second one. In fact, it's much easier to prove the second one. Okay. So now, what does that tell us? That tells us that any polynomial, any complex polynomial, has n roots. So I mean like degree f number of roots. But some may be repeated. Right? It doesn't stop us from saying there's an x minus 1 times x minus 1. Right? Some may be repeated. Mathematicians will just replace this phrase and say up to multiplicity. Multiplicity. Okay, so let's talk about a nice lemma, that tells us whether there are repeated roots. Okay, this is kind of unrelated to complex numbers, but it works for it works quite well. So this lemma is this: fx, well, a complex polynomial has a repeated root if and only if, so it's an equivalent statement, it goes both directions, f and f prime, the derivative of f, if you've learned that, it's okay if you haven't. F and f prime have a common root. Have a common root. The derivative. Okay, the forward statement is easy if you know your derivatives well. If fx equals x minus r squared times some gx, so a repeated root basically, then f prime x equals 2x minus r gx plus x minus r squared g prime x. This is the product rule. And you can see a common factor here. Common factor, common factor. So the forward direction is easy if you know your product rule. The backwards direction, a little bit harder, but I think it's still understandable. So instead of proving the other direction, I'll just prove the contrapositive. So if fx has no repeated roots, then fx equals a constant times x minus r1, x minus r2, blah, 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 x minus rn. Where r, I are all distinct. if f has no repeated roots, and this. Now, I'm going to apply the n variable, well, the n term version of the product rule. It's actually quite simple. For those who know calculus, I'm sorry for those who don't. You can skip this part if you don't know what I'm saying. For those who know calculus, the product of two functions, f times g, I should really write f times g, otherwise people might say it's a convolution. F times g prime is f prime g plus f, in fact, I'll just write f g, why not? Plus f g prime. For three variables, actually, it's very simple. You just, same thing, you just apply the prime to every single term. F prime g h plus f g prime h plus f g h prime. What is f prime to f? F prime is a derivative, so it might not make sense to you if you haven't learned calculus yet. So f prime is what we call the derivative of f. Oh, okay. So your question was, what is f prime? This is a product rule. This is the product rule. Someone asked just now. Derivatives are, well, it really depends what you mean by commutative. So derivatives are additive, that's for sure. But derivatives are not multiplicative. For example, if you take the product, you take the derivative, it's not equal to f prime g prime. It's equal to this thing. It's a product rule. But I'm just introducing this product rule before we move on the statement. So it's a separate thing I'm saying now. And for the four variable version, you can guess it probably. F E F G H I. Okay, calling a function I is a bit weird. F G H P is f prime g h p plus f g prime h p plus f g h prime p plus f g h p prime. It's easy to prove this. Just use simple induction, right? Because this is literally just f times the new function gh, and then you just continue doing. So if you have this product rule, okay, so f prime x is, how do we write this? Well, I'm going to write it like that. In fact, it's like c and then x r minus r2 dot x minus rn plus c x minus r1 x minus r3 dot x minus rn. So every term we skip the ith term, right? That makes sense, right? Because the derivative of x minus r is just 1. Maybe we can write this more concisely. So this is the sum from I equals 1 to n of the product, times c of j not equals to I x minus rj. Well, now it's a simple thing to see. If I plug in x equals any ri, f ri, well, for those terms who have an x minus ri inside, they all vanish. They all vanish because x minus ri, x equals ri, so they vanish. So the only term that doesn't vanish is the term that doesn't have the ri. So that will be ri minus r1 dot ri minus rn, where inside they skip ri minus ri. So this is non-zero. That means any root of f originally, I plug it into f prime, is not zero. That means they don't have a common root. So we're done. Okay, so far so good. So these are both directions of the proof. Okay, So for example, the example I gave in the handout, x to the 40 plus x squared plus 100. So how do we know if there's no repeated roots? Well, the derivative is 40x to the 39 plus 2x. Oh wait, did I write it wrongly? Oh well, okay, no. Okay. Well, I can just check whether f prime and f have common roots. Well, the roots of f prime is easy. Roots of f prime. So it's x 40 plus this equals 0 divided by 2 x equals 0 or x to the 38 equals. Well, what does derivative have to do with complex numbers? Well, if we will see, well, so yeah, technically it doesn't have to do with complex numbers, but it will be quite useful later when we talk about roots of unity, because this is a condition, it's a nice condition to see whether or not a function, a polynomial, has a common root. That's what I'm saying, basically. So it's a very nice way to determine whether a polynomial has a repeated root. Okay, so we have this. And basically, you just plug this back in here and just prove that it doesn't work, right? Like, if this really were to be 0, we just derive a contradiction. So x squared x to the 38 plus 1 plus 100 is 0. X squared 19 to the 20 plus 100 is 0. You can kind of see, obviously, there's a contradiction coming up. So x squared is some weird number, and I'm pretty sure x to the 38 won't be minus 1 over 20 in that case. So it's a nice condition. So can everyone see what I'm doing? I just say whether these two can be simultaneously 0, and in fact they can't. It can't be simultaneously 0. You'll get a contradiction somehow. So you know that this thing has 40 completely different complex roots. I mean, you know they are not real because this is obviously greater than 0 for all x. Completely different complex roots. So you can proudly say this has 40 roots without any discrepancies or whatever. Like if you say 40 roots, some people might say, okay, with multiplicity or not. Okay. Okay, some of you might ask, just now I said we haven't talked about derivatives in complex functions yet. So why am I assuming that the derivative exists? Which is a very good question. Because what I'm doing here now, I'm not exploiting any calculus properties actually. So I can simply, sorry. I'm not really exploiting any calculus properties. I'm just using the product rule here. Okay, it might be a calculus property, but hear me out first. Might as well forget calculus. And say if a polynomial has this form, and then I define f prime to be this n a n x n minus 1 plus blah 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 plus 0. So basically the xk becomes k to the k minus 1. But it doesn't matter if I don't know calculus or not. I'll just let this thing be called the derivative, and I won't tell you what the significance of it is. Like, I won't tell you this is related to the tangent of the graph or the continuity or whatever. I just forget all of that. I just say this is just what I define to be the derivative. And then the product rule will hold. In fact, the product rule actually is, you can prove it without using any limits or calculus or whatever. With just this simple definition, you can prove the product rule without use of limits. It's just that if we know calculus, it just helps us see that the product rule must be true anyway, even if this thing has no significance in graphs. So the product rule is true for calculus, but you can prove it without it. Right? In this whole proof, I've never used any limits. I've never used any differentiation or integration or whatever. No. I mean differentiation, yes, but I can define this new thing to be a differentiation. Because this totally works in complex numbers, right? There's no ambiguities for this definition. Okay. I hope that makes sense. Again, if you have questions, please ask. Please ask. Please ask. Okay. Now, another question that I wrote in the handout. How many solutions does this have? So C is a complex number, a fixed constant. How many functions, how many solutions does this have? Like how many distinct roots does it have? Let's see. Well, it has degree n. So first of all, it has at most n roots. Well, at least one at most n. Okay. I'll write this as xn minus c equals 0. So this is a polynomial now. Well, f prime x is n times x to the n minus 1. The only roots here are 0. Just 0. So does this f prime have a common root with fx? Only in one case, right? Where c is 0. Does that make sense? So we're trying to apply that criteria, whether or not f and f prime have a common root. And apparently f prime has a common root with f only and only when c is 0. Because the roots here are 0. If you plug it back into here, there is only 0 when c is 0. So when c is not 0, there are n distinct roots. N distinct roots. When c is 0, well, x to the power of n is 0. That's obvious. There's only one root. Just x equals 0. So one root. But it's technically n roots, but then it's one root repeated n times. Okay. So let's look at the application of this. And we're going to look at this function now. X to the n equals 1. So the case where c equals 1. Now, first of all, can we say something about the magnitude of x if you want to solve this? What's the magnitude of x? What's the only possible magnitude of x? Oh yeah, just now, by the way, after the multiplication and the multiplication magnitude and argument thing, I probably have to write it down explicitly for you to understand. So I was saying, if you multiply two complex numbers, their magnitudes multiply. So you can write it like that. And the arguments add, right? The arguments add. Oh, sorry. Argument of uv is argument of u plus argument of v. In fact, I should be more precise. I should say this is mod 2 pi. So once I go around 2 pi, I just say it's the same number. Okay. So x to the n is 1. Okay, so I should also say n is a positive integer. N is an integer. So what's the magnitude for x if there were a solution for this? But we can see if I apply magnitude on, if I apply absolute value on both sides, well, the magnitude of 1 is just 1. So, and this thing, by the property above, is equal to the magnitude of x itself to the power of n, right? Because x to the n is just x times x times x times x times x times x. And the magnitudes multiply. So this is an easy function. This is an easy equation in real numbers. The absolute value of x is always a non-negative real number, right? So this is not a complex equation anymore. This is just a real equation. What number to the power of n is 1? Just 1, right? Okay, some might say -1, but remember, absolute value of x is only non-negative. It's always either 0 or positive. So that's the first thing we can see. So property 1. All roots are magnitude 1. Magnitude 1. Well, have magnitude 1. Okay. So if they're magnitude 1, they must be e to the I theta for some theta, right? E to the I theta for some theta. And we're going to solve for theta now. We're going to solve for theta now. So we want, x. That equation was x. So x to the n equals 1. So e to the I n theta equals 1. So look, what kind of angle after multiplying by n goes back to 1? Well, what's the angle of 1? 1 is here. 1 has argument 0, right? 1 has argument 0. What kind of angle after multiplying by n will get back here? Well, first of all, why do we use e as the base of complex numbers instead of any number like 2 or -1? Okay, another good question. Very good question. Did I have the power series thing still here? Oh, I deleted it, right? Because we use the series for e to the x. So we use this thing, right? Like this power series, well, in fact, if I plug in 1, I get this number. 1 plus 1 plus 1 over 2. Sorry, the pen is very laggy. So the fact that we use this power series to prove it, that means it must be this function. It's not 2 to the x. 2 to the x is something else. Probably like e to the x ln 2. So you substitute ln 2 here. So the base must be e, because we're using this function e to the x. And this function is literally 2.71 something to the x for, well, if x is an integer, for example. So it's a function whose restriction onto n gives literally 2.718 blah blah blah, the number e to the power of, why is my pen so slow, to the power of x. So we want a function that kind of like is consistent. Does that answer your question? Okay, nice. Okay, so how about here? What kind of angle after multiplying by n, like rotating n times, gets back you to here? What gets you back to here? Well, the first one of the solution is easy. The zero angle, right? Zero angle times n, you're still at 1. Any other angle times n? Well, yes, we can look at 1 as 2 pi, right? 2 pi argument. So we can say 2 pi over n also works. So 2 pi over n is like, if you cut this angle into n pieces, if you cut this angle into n pieces, you take, so this is the angle, 2 pi over n. If you multiply by n, it just rotates n times. The argument times n. And it gets back u to 1, so that's also fine. In fact, can we go further? Even 4 pi over n works. And so on and so forth. Well, we can't go on forever. If we go on forever, we're just kind of looping back to itself. So what's the last one that doesn't cause a repeated thing? And the answer is n minus 1 times 2 pi over n. So that multiple. If we go one more step, it becomes 2n pi over n, which is 2 pi. Like if you do one more step, it's 2 pi, but 2 pi is just 0, right? It gives you the same thing for e to the I theta. So these are some solutions. Some solution. I haven't agreed that it's all of them yet. To the equation. Well, I mean to the equation e to the I theta n equals 1. So x to the 2 pi over n times k, where k is 0 to n minus 1, are some solutions to the function x to the n equals 1. Now, can anyone tell me something that we can say from this? Are they all of them? Are there any other ones? Why or why not? Now look, x to the n equals 1. What's the degree of this polynomial x to the n minus 1? It's n. You can only have at most n roots. But we have already found n roots. Sorry, this is e. This is e. We have already found n roots. So that means even though we did this by guessing, I mean you probably don't have to guess, you can just write this as 2 pi k and whatever. But it's easy to guess this n solution. But then you know by that theorem that we've discussed so far, we know that there's only at most n roots, but we already found n roots. That means that those are all of them. So those are all of them. Is that clear? So e.g., n equals 5, maybe. So the 5 solutions, they lie on the unit circle. So the first solution is 1, and then we're going to cut this into 5 parts. Like that, maybe. Yeah. So this is e to the 2 pi I over 5. Oh, hang on. Yeah, oh yeah, sorry. Correct. E to the 4 pi I over 5. E to the 6 pi I over 5. E to the 8 pi I over 5. Wait, this doesn't look right. 1, 2, 3, 4. Oh yeah, it does look right. Okay. So 5 roots. And there's this beautiful symmetry going on. These are called the roots, the 5th roots of unity. 5th roots of unity. So unity is just a fancy way of saying 1. So there are 5 roots of unity. These are called the 5th roots of unity. But there are 5 5th roots of unity. Can we write this in a nicer way? I can let this one, the one with the smallest positive argument, to be, let's give it a new symbol. Let's say zeta n. Zeta 5, because it's the 5 case. Zeta 5. Then all of the other ones are just zeta 5 to the power of 2, zeta 5 to the power of 3, zeta 5 to the power of 4, and this is the zeta 5 to the power of 5, zeta 5 to the power of 0, same thing. Well, there's a name for this. You can look at it in the handout. It's called a principal root, but you don't have to know that really. But you can just let this be zeta, or you can just name it whatever you want. You can name it omega, theta, chi, or whatever. Okay, so does this make sense? Yeah, zeta 5 to the 5 is 1. But because zeta 5 is the solution to x to the 5 equals 1. So yeah, so all of them comes together. And you can see the symmetry is like, it's because if you rotate every single point here 5 times, you get back to 1. So beautiful symmetry. Okay, now how about we look at the general case? X to the n equals c. So now c is a complex number. Let's just write it as a real part, a magnitude part. Oh, it's laggy. Sorry. Let's say r times e to the I theta. So these are fixed, okay? These are not things that we want to solve. These are fixed. These are fixed numbers. And we want to solve for x. Okay, I'll just give you the solution. And actually no, I'll just leave it to you as an exercise. I'll give you a hint. I mean it's already in the handout, so but the hint is you find one solution to this. After you find one solution, you can get all of them by multiplying by this zeta to the n, zeta sub n. Because you know if x n equals c, then x to the zeta n to any power to the power of n is also c, because this kind of is equals to 1. So after you find one, you just multiply by the n roots of unity, you get all n of them. But if it's easy to find one, right? Actually, no, I already finished saying the proof by doing that. It's easy to find one. R to the 1 over n, e to the I theta over n. That's one solution. So we're done. Just take this one and multiply by a root of unity. Does this make sense? Does any questions? Oh, we have 15 minutes left. So hopefully I can present the proof of the every polynomial can be split into n linear factors theorem. Okay, so if no questions, again, I still have one more thing to say. So let's look at x to the n equals x to the n minus 1. We know that the roots of this is the whole root of unity, the n numbers, right? So you can actually factor this into something like that. So x minus 1, x minus e to the, I'll just use this notation. Why not? Like this. Like this. Well, n of them. So this is a identity that you might give up if you just see this without thinking about why. Like if you ask this, if you ask this and you cover this up, and someone tells you to simplify this, you might literally go and calculate every single coefficient, whatever. But another way of thinking of it is all of these roots satisfy x to the n equals 1. But since the degree, both of them are also n, that means they are equal. X to the n minus 1 is equal to this. So that's another strategy that you can use. You can guess the solution first and then use some arguments to back it up. For example, like the degrees are the same or whatever. You can guess the solution first and then yeah. So not every single solution has to be like you have to kind of do some technical things onto it. Actually, most things require you to think of a way of explaining what you do, or like what you consider, what you introduce, the variables and whatever. Okay. Also, a last thing to say is the thing about square roots. So for example, 1 minus I squared if you write it out, I think it's equals to minus 2i. Okay, but also I minus 1. Also I minus 1, because minus 1 squared is 1, obviously. Well, unlike in real numbers, where we can define this thing very, very nicely, like this is supposed to be the solution, but well, the definition is the solution to x, k squared equals to x, where k is greater than or equal to 0. This is the definition for square root in the real numbers. I mean, you can extend this like 1 over n. So this is the solution to k to the power of n is x, where k is greater than 0. But in complex numbers, you cannot really have this thing, right? You cannot talk about inequalities for complex numbers. So there's no inequalities in complex numbers unless you do some very weird thing to define like what you mean by greater than. So no inequalities in complex numbers. So how do we say which one is the true square root of minus 2i? Do we say it's I minus 1, or do we say it's 1 minus i? Like if we say square root 4, we will say it's 2. We wouldn't say it's minus 2. We will say like x squared equals 4, x equals plus or minus the square root of 4. And then that's plus or minus of 2. But here we don't know which one to choose. And therefore, writing square root needs some caution. So either you define a well-defined definition of square root. For example, for roots of unity, you can do that. For roots of unity, you can define the nth root to be the one with the smallest positive argument. So that's fine. That will be a well-defined function. But for general cases, it doesn't make sense to choose one. Like unless you use some very crazy rule, which you can eventually. But we just try to not use the square root symbol as much as possible, unless you really define it well. That's why this is confusing. I equals square root minus 1. But you can probably say it's well defined by using the smallest positive argument definition, because you know the two solutions to x squared equals minus 1 is I and minus I. I has a smaller argument, so you probably can say I is square root minus 1. So that's what we call the principal root, the one with the smallest positive argument. But I'll just try to not use this symbol, square root minus 1. Because if you do, you have to do more you have to do more explaining. So we have to use all of these things with caution. We have to know what we're doing. Like some people might say, okay, 1 is equals to the square root of 1 is equal to the square root of minus 1, because minus 1 times minus 1 is 1 times 1. But it's equals to minus 1 to the minus 1. It's I. Sorry, it's I times I. It's minus 1. So why? So what the heck? So that's why don't use the square root symbol. It can be confusing sometimes. And if you use some very archaic definition of square root, you have to make sure what holds and what doesn't hold. And I think, if I remember correctly, if you use the principal root definition, this doesn't hold anymore. So square root AB is not equal to square root A times square root B. Okay, any questions so far? Any questions? We finished the lecture part. The exercises part, again, you can try it yourself. If you have questions, if you want a hint or whatever, you can just Discord me or WhatsApp me. Any questions? Any questions? I hope I explained complex numbers well. And If you have any confusions, please ask anytime. So there is an exact way of understanding complex numbers. Like there is no ambiguities. Like some people might give this example and say, oh, okay, so therefore square root AB is not equal to square root A times square root B. But those are kind of like ad hoc kind of like rules. But gonna have to know what really happens in the set of complex numbers in order to understand all of this. Okay. If no questions, I will be giving an attempt to prove to you the fundamental theorem of algebra. In particular, I'm going to prove this statement for you. Any complex polynomial has a root in C. Okay. And it's actually, I don't think the proof is hard, actually. It's quite, you can follow it quite easily, I think. Well, so let's say fx is an xn plus blah 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 plus a naught. So a few recipes that you have to know. So remember, we say the first term always dominates. I mean, that happens in the real numbers, but apparently that happens in the complex numbers as well. When your x is really far away from the origin, really, really far away, then this term will dominate. The other terms will be like negligible to him. So that's one ingredient you have to know. Okay. Of course, you have to make this more precise by doing triangle inequalities, absolute values, whatever. But I'll just leave it as that. So remember, okay, never mind. Another thing is we can WLOG assume this is not zero. I mean, if it is zero, that means fx has a root x equals 0, right? So we assume the constant term is not 0. We assume the constant term is not 0. Is that fair? Okay, so now we're going to prove it. Okay. So here's what we're going to do. I will let x be r times e to the I theta. Okay, I'll let x be r times e to the I theta. Now, let's see what happens when r is very, very large. So, okay, first of all, we cannot really draw a graph for complex functions because otherwise we have 2 dimensions for the input, 2 dimensions for the output. There will be 4-dimensional graph, right? So we cannot really do that. What I'm going to do here is, this is the graph of the outputs. This is the graph of the outputs, the image of f. So for example, let's say x equals to 33. Then I'll just plot a point for you to show you where f33 is. Okay, so if that makes sense, let's continue. Where r is large, okay, okay, let's just assume a, sorry, not greater than 0. Actually, never mind. Ignore this. So when r is large, fx is approximately an to the xn. Okay, an to the xn. Now, if I fix r now as the very large number, now I vary theta. So as theta goes from 0 to 2 pi, it kind of like is a continuous input, right? And if we plug it in, we should get points on a very, very, very large curve that's very far away from the origin. Okay, does that make sense so far? So these are the points of f r to the I theta. very far from the origin. Far. So this is, I'm varying theta basically, like here maybe theta is 0, theta is 1, theta is 2. In fact, it's continuous, so it's actually a whole curve. Okay. So this curve is the r equals a very large r case, and then we have a parametrization of theta here. So that's where r is large. Where r is small, in fact close to 0, then fx is approximately a naught, right? If r is small, technically a naught dominates when r is small. So when x is close to 0, then fx is approximately a0. So first of all, a0 is not 0. So a0 is somewhere on the plane. Let's say this is a0. Let's say this is a0. That means for very small r, the curve is somewhere like that. Okay. So this is r equals small. And again, this is again a parametrization of varying theta. So you get this curve, a very small curve surrounding a naught. Now, can anyone see how we can prove there's a root? So what does it mean there's a root? R is the magnitude of x. The magnitude of x. So when the magnitude of x is large, it lies on this circle. Very large, I mean it's not a circle, sorry, a curve, very far from the origin. When x is small, it lies on the curve very, very close to a naught. When x is small, I mean when the magnitude of x is small. So what does it mean when f is a root? F has a root. That means f has there's some x that passes through this origin, right? So let's see. The r equals large case, r equals small case. Let's just continuously deform x. Let the magnitude be smaller and smaller and smaller and smaller and smaller. From the large case, I gradually transition into the other regime, which is the small case. Then this curve will be smaller, smaller, smaller. In the end, it should go here. It should go here. That means at some point, at some magnitude, it must pass through 0, and that's the proof. So this is a root. So this is very vague proof about like curves and whatever, but you can write this out rigorously if you want. Of course, you have to make sure you know continuity and all those things. So for the large magnitude of x case, they lie on this curve, and of course, any point on this curve is achievable by varying theta. For small magnitude of x, it's in this small curve. So if we transition from the large magnitude to small magnitude and kind of cover all kind of possible x's, at some point it must cross the origin in order to get to a naught. And when that happens, that corresponding x and that corresponding theta on this curve is a root for f. And that's how you prove this statement. Any polynomial has a root in C. Okay, so it's 1 now. Any other questions? Oh, I hope this is an interesting topic because it's fairly new for most of you. The reverse of the origin to a naught. Yeah, kind of. Okay, so any questions? What did I do again? Any questions before we end the class? You can try the practice problems. No, then I will end the class here. Thank you all for attending this class. Well, I'll see you like probably next camp if that's still working. So I'll stop the video. Okay, then goodbye.